Hello, everyone. In this video, we are going to present ARO-Net, learning implicit fields from anchored radial observations. We introduce anchored radial observations, ARO, a novel shape encoding for learning implicit field representation of shapes that is category-agnostic and generalizable. Given any shape, our main idea is to use a set of viewpoints, called anchors, to capture partial observations for reasoning about shapes. We design a deep neural network based on ARO to predict the occupancy value of a query point in space. We first construct a number of anchors in space, named AI, and cast a cone from the anchors to query point to obtain observations, called OI. The network encodes and aggregates these observations, and then performs implicit decoding to predict the occupancy. This figure shows neural 3D reconstruction from sparse point clouds by ARO-Net, trained only on chairs. ARO-Net can even be trained on only one model like the fertility to reconstruct of a variety of shapes. In 2019, OCCNet and IMNet concurrently introduced the coordinate-based implicit neural representation. In these early works, the shape encoder and latent code employed for occupancy predictions only modeled global shape features. The resulting learned representations were unable to reconstruct fine geometric details. Then, convolutional occupancy network and points-to-surf were proposed to extract the local features of given point codes to better reconstruct the details. Different from these two works that encode the neighborhood information around query point as features, our ARO-Net encodes observations from anchors to query points. We use a toy example to demonstrate the difference between ARO-Net and representative models based on global or local shape encodings, for example, OCCNet and convolutional OCCNet, for the 3D reconstruction task. All three networks were trained on a single sphere shape, with a single anchor for ARO inside the sphere. When tested on a cube, the results show that both OCCNet and convolutional OCCNet exhibit more memorization of the training sphere either globally or locally, while the ARO-Net reconstruction is more faithful to the input. Let's discuss the technical details of ARO-Net. First, we introduce the relationship between anchor visibility and point occupancy, which is the basis of our ARO representation and ARO network. Here, we first define the visible regions of different anchors, colored in blue and green for interior and exterior anchors, respectively. When anchors are all interior and fully cover the shape, a query point is inside the shape, is equivalent to, it is covered by at least one radial observation. When anchors are all exterior and fully cover the shape, a query point is inside the shape, is equivalent to, it is not covered by any of the visible regions. When some anchors are inside the shape and others are outside, we can turn the situations into B and C, according where the query point is. To summarize, if we have a set of anchors that together observe the entire surface of the shape, then their visible regions together can fully determine the inside and outside regions of the shape. If the shape is only partially observed by the anchors, we don't know whether each anchor is inside or outside the shape. We introduce ARO-Net to predict the occupancy from incomplete information after training with data. In this figure, the input point cloud are drawn in gray, anchors are drawn with different colors. Given a query point X shown as the red star, for each anchor AI, we can compute the relative position of X to AI as Ri. Next, we create a cone with apex at AI, and Ri as the axis to get the nearest K points as OI, which is defined as the radial observation of AI relative to the query point X. Each OI is then passed to the pointnet to get the corresponding embedding feature Fi. The relative location Ri and its norm are further concatenated to get a local feature. All the local features relative to all the anchors are then passed to an attention module and finally decoded into an occupancy value. We use Fibonacci sampling at different radii to construct the anchors. For more details, please refer to our paper. Let's move on to the experiment section. ARO-Net is able to reconstruct both global structure and local detail well, including sharp features as UNDC. And its results exhibit the least amount of artifacts in terms of holes and noise. This figure shows more results on ABC dataset. Compared to existing methods, ARO-Net produces the most complete, artifact-free results with faithful reconstruction of fine details. In the airplane results in second row, it is worth observing that ARO-Net managed to reconstruct the left side turbine from extremely sparse points, while other methods all completely missed it. This figure shows more results on ShapeNet dataset. As shown in these tables, ARO-Net exhibits a clear advantage in Hausdorff distance and OCCIOU, and produces the overall best performance by ranking the first in 3 out of 5 metrics, IOU, EMD and HD, and ranking the second in 1 metric, LFD. For the remaining CD metric, ARO-Net is still a close runner-up. ARO-Net also exhibits superior robustness to sparsity of input point clouds. Once trained with 2048 point input, ARO-Net can produce quality results with sparser inputs without retraining. When the number of points decreases from 2048 to 512, the reconstruction quality of both UNDC and points 2 surf degrades dramatically, as also reflected in the CD and IOU metrics. By contrast, ARO-Net yields the highest level of robustness both visually and quantitatively. Other than Fibonacci sampling, we also tried 2 different sampling strategies, uniform and grid-based sampling. In uniform sampling, we randomly sample M points in a unit sphere as anchors. In grid-based sampling, we randomly sample M grid points of a unit cube as anchors. Through experiments, we found that our layered Fibonacci sampling achieves the best performance. As a stress test, we train the networks using only one 3D shape, fertility, with rotation and scaling. As we can see, OCCNet clearly overfits to the training shape. CONVONet generalizes better but produces overly smoothed results. In contrast, ARO-Net reconstructs both global structures and fine details better than the alternatives, with consistency over the shape variety. When choosing the number of anchors, there is a trade-off between reconstruction performance and computational cost. We set M to 48 by default. We also tried to replace our attention module and implicit decoder with the much simpler MLPs by IMNet. The similar performance numbers indicate that the superior results by ARO-Net are predominantly owing to ARO rather than the decoder architecture. One limitation of ARO-Net is that its computation cost grows with M linearly. In addition, its performance depends on the number and placement of the anchors. Further research into anchor selection, even learning, is needed. We also plan to use more efficient spatial search data structures to find closest points. Thank you for your listening.